Welcome to Real Learning Center. We're going to basically move on to the second topic today. In the first topic, we talked about potential and kinetic energy. We were dealing with energy. So the second topic, we're going to deal with some new words called work and power. These words are very much known to us. It is just that the meaning of these words in physics may be slightly different from our day-to-day life. So let's look at what are these work and power. Okay. So today, let's talk about, whenever we talk about the word work, so in physics when we say work, is it same as when we say work in normal day-to-day life English? So let's take a simple scenario. Okay, why are you saying, why are you playing all the time? Why don't you do some work? All children must have heard this statement from their parents or the teachers. So, however, you must be happy that in physics actually, playing is also work. So, it's not just some other work. Even playing is also work as per physics. You know how? Because work is defined a little differently in physics. As per physics, work is said to be done, okay, by a force on a body. Okay, work is done by a force on a material, okay, on a body, if it actually displaces the body in the direction of the force. In whichever direction the force is there, it actually moves the body. Or if it actually changes the speed of the body. In both cases, we say work is done. Okay, and please carefully look at these two statements. Okay, any other case is not considered to be work. The work is as simple. If you just move the body using certain force in the direction of the force, that's important, and or at least some component of the movement should be there in the direction, okay, and the change in the speed, both of them are actually said to be doing work. Okay, so now there is a formula, okay, that we can calculate the work. Work is not just some useful work, that kind of a qualitative measure in physics. In physics, work is basically a quantitative measure, means there are numbers to this. Work done is the word that we use. Okay, work done will be equal to force into displacement. That means basically, if you know the force in newtons and the displacement in meters, you can multiply that and get the work. So we always use the word F dot ds for this. Okay, you will come to know about why we call F dot. Ds is the displacement. Okay, dot is a kind of multiplication, which is slightly different from the multiplication that we know about. Okay, it's called a vector dot, and it's used in vectors. It's called a dot product. Okay, so don't worry about that. We will understand the meaning of that in a short while. So W is equal to F dot ds is basically the way we compute work. Okay, so now let's see some situations where work is done. Okay. See, let's say this person is actually carrying, he's dragging the suitcase along with him. So when he is doing so, he actually does the work because he is applying a certain force and he is moving in the direction of the force. He is taking the bag in the direction of the force. So he is doing some work on the. So work is done by the person, and on what? On the bag. So he is doing the work on the bag. That's how you look at it. What about this? Is that guy doing work on the wall? If you look at it, actually he is really finding very hard to do this. It's not very easy. He's pushing the wall. But the wall, is it moving? It's not moving. So force is there, but there is no displacement. So when you do force into displacement, this will give a value of 0. So this is no work done. Okay, though he is trying really hard, the work is not really done. Okay. So look at this. This guy actually is a weightlifter. He has lifted a huge weight. While lifting the weight, he actually was doing the work. Once he keeps the weight on the top of his head like this, he's really facing it difficult and with a great of effort he is holding it. His muscles are all strained, but still he is not doing work because he is not moving anything. Okay, there must be force and the displacement, then only work is done. Okay, so let's look at the scenario of let's say Earth going around the Sun. So when Earth is going around the Sun, you can see that there is a force. Now see, the force need not be always a contact force. The force can be any kind of force. Here gravitational force. So gravitational force is pulling the Earth and Earth is moving. So can we now say that the work done by the gravitational force is equal to force into the displacement at any point in time? So now here is a slightly careful study is required. So if you look at this, I will stop it at some point and just a snapshot, and I will show you the direction of the force. Direction of the force is basically towards the center. It is pulling it towards the center. A force that pulls towards the center is called a centripetal force. Okay, that we have seen in circular motion. And the body is actually moving not towards the center. On the other hand, the body is moving actually, if you see, in a tangential way. Okay, that means a displacement is in a different way, is perpendicular to the force. Okay, no component of the displacement is towards the force. So if you do F dot ds in this scenario, okay, displacement, you actually get 0 because it is not moving in the direction of the force at all. So we can say a centripetal force generally is not doing any work. It doesn't do work. Centripetal force doesn't do work. Remember this. Okay. So this is one of the special cases of you see that it is moving but there is no work done. So now let's look at basically how to actually do some computation of this work done. Can we calculate? Okay, how to calculate? A simple examples. Here is a person who is actually pushing the box, a huge box, with a 5 Newton force. Okay. So he is pushing with a 5 Newton. Force we measure in newtons. 5 Newtons force is pushing, and it is moving, and it has moved by a distance of 10 meters. Now we know the force is actually 5 Newtons and the displacement is 10 meters. Now if you actually multiply that, what will you get? 50 joules. So this is joules. J is joules. That is the unit of work done. Okay, remember, force into displacement is basically giving us work done, and the unit is joules. So work done is 50 joules in this. So very straightforward, simple way of calculating. Just have to multiply. But it gets a little complex. Okay, when you go see some changes in the what, you keep watching that. I'm going to do some change. So here again he is pushing. But when he is pushing, no, he is not so efficiently pushing it. Okay, he is not just pushing like this. Okay, he is pushing with some force on the top. So his push, the force, is actually not only towards the direction, but also in this direction. It's going down. It is pushing it down also. In his force, there is a part of the force which is making it go in the horizontal direction. There is a part of the force which is pushing it down. So he is not doing it efficiently. In such scenario, if you want to calculate, you here again assume that he actually does push it by 10 meters. Then the work done, will it be basically 5 into 10, which is 50 joules? That's the question. So the answer is no, that is wrong. So we have said very clearly that force into displacement, okay, but in the direction of the force. So how do you compute that? So it is done in two different ways. I will explain to you both the ways. Okay. So first way is, let's say you take the force, okay, and you saw that the force is in this direction. Okay. Now I will actually move that whole system. This is the x-axis in this. I have taken x-axis in this direction, y-axis is downwards. I can take x-axis in any way we want. Okay. So x-axis I am taking horizontal towards left, and y-axis like this. Okay. So now if I keep it like this, for example, so you can see here that it makes certain angle. Okay. Now actually this is the force, and that is x and y axis. Now we have the way to calculate what is the force which is acting in the direction. See, look at force acting in the direction of displacement is how much. We can calculate that. Force that is acting in the direction of displacement. How do I do that? I take the displacement is horizontal. So x-axis is displacement. Now the force is like this. So from the force I will draw one perpendicular to the displacement line. Okay, displacement is in this direction. So I will take a a vertical line, a perpendicular I will draw to that line. Okay. And then I will actually measure the length on the x-axis. So that length, let us say, okay, I measured it. This was 5 and that is 4. So it means 4 newtons. Now I will take that number that is in the direction of the displacement. So now I will write the my work done equation little differently. See, I will write it as work done is equal to force in the direction of the displacement into displacement, and I will say work done is equal to 4 into 10, which is actually 40 joules. Now that is one way of doing. So what did I do here? I actually took it, the force in the direction of the displacement, how much it is, I measured it by drawing a perpendicular to that. Okay, now I can do the other way around too, which is I will take actually the force as it is and the displacement in the direction of the force. You can do that too. I can take the displacement in the direction. How do I do that? So now I will take the displacement vector, okay, and keep it here. So that is my displacement vector. Okay. And I will find the direction of the force. This is my direction of the force. So I will also move that there. Okay, just for clarity, I will move it on the left side. Okay. So now the same thing I will do. I will take the displacement vectors component in the direction of the force. So I will now go to the displacement vector and from there draw the perpendicular to the force direction. After drawing in that direction, I am going to put the line here and measure it. So initially this was actually 10 meters and this is the second one. I measured it to be 8 meters. So now what I will do is I will substitute this 8 meters in the place of displacement. So force I will keep as it is. Force doesn't change now. Force is 5 newtons and displacement is 8 meters. So you get 40 joules. So remember, the previous one also gave me the 40 joules. That means you can do force into displacement in the force into displacement in the direction of force, or force in the direction of displacement into displacement. Both of them will give the same value. This is what we call a dot product. Okay. Now don't worry about that. So let's now get into basically the relationship between work and potential energy. Is there a relationship? See, we studied potential energy. So now we will find out, is there a relationship between work and potential energy? So let's basically take a weight and a barbell basically, and this is in the position 1. Okay, now if you have already lifted to some height, so now we are going to basically find out what is the potential energy of it. How will you find out? So we know the formula. So first let's measure the height. The height, the mass is 10 kg. And the height actually is that's a 1 meter. Okay, 1 meter height you have already lifted. Now, what you are going to do is you are going to calculate potential energy of the barbell. So how do you do it? You need one more variable, which is basically how much force you are resisting to weight. So there is an acceleration due to gravity, which is g, which is 9.8 meters per second square. If we actually multiply all these three, we get potential energy. Potential energy is nothing but mg into h. So in the place of h now I will use 1 meter. So that will basically become 10 into 9.8, which is nothing but 98 joules. We get the potential energy of this to be 98 joules when it is at the position 1. Now we are going to move it to the position 2. Okay, once it is moved to the position 2, we want to calculate the potential energy there also. So for that we need the height again. So we calculate the height here to be 2 meters. So now I will apply the same formula, P is equal to mgh, and calculate the 10 into 9.8 into 2 this time, because it is 2 meters. And we will actually get 196 joules. So PE1 is the potential energy at position 1 and PE2 is the potential energy at position 2. Now what we are going to do is, now since we actually moved it from position 1 to position 2, we did some work. Okay, we moved the object from position 1 to position 2 using certain force against the gravity. Okay, and we did some work. How much work did we do? So we did work based on our formula, work done is equal to force into displacement. What is the force? The force can be calculated by mass into acceleration. Newton's second law. The force is basically m into g. The acceleration here is g. Okay. So the force that you applied, okay, you look at this, m into g is the force with which the earth actually is pulling it down. And for you to take the barbell upwards, you need to apply a force which is equal to m into g. Slightly more, minuscule more than m into g. Then only you can move it up. Okay. Otherwise, it will not go anywhere. Okay. That is why we have taken it as m into g. Okay. And that is the force. And then displacement is basically 2 minus 1. But this is to this totally 1 meter we moved. So we get it as basically 98 joules. 98 joules of the work done in moving from here to there. Now, after looking at this work done, I am going to now calculate the potential energy difference. Okay. So what is the original potential energy PE1? What is the final potential energy PE2? So change in potential energy is nothing but, we call it we use a word called a triangle and PE, which is a delta P. We read it as delta potential energy, means change. Delta is always used for change. Okay. So delta potential energy is equal to PE2 minus PE1, which is 196 minus 98, which is equal to 98 joules. Now, you can very clearly see that this 98 joules and that 98 joules are exactly equal. So what was the first one? The first one is work done. Second one is change in potential energy. We can clearly say that delta P, that is change in potential energy, is equal to work done. This is one very interesting understanding that we have got. So there is a relationship between potential energy and work done. So change in potential energy is equal to work done. So this is in the existence of a force field. So we have a force field here, which is the gravitational field. So within the gravitational field you move something. So in such scenarios you use this kind of a relationship. Whereas when you do not have a force field, okay, now you cannot apply this. So you apply another basically relationship between energy and work done. Let us say I am in space. Okay, in space, anything can move on its own. If it is having certain velocity, it will be actually moving. This is my space shuttle, which is moving in space with a velocity of 10 meters per second on its own. There is no fuel required to go at a constant velocity. That is what Newton said in his first law. No fuel required. Okay, unless it is compelled by an external force, it keeps moving at 10 meters per second. Now, what I am going to do is I am going to calculate what is its kinetic energy. It will have, because it has velocity. So we can calculate it to be using our formula that we learned in the previous video. So Ke, kinetic energy, is equal to half mv square. Okay. So half mv square will substitute and it will become 500 into 10 square, which is 25,000 joules. Right? Its mass is, let us say, 500 kg. Space shuttle is heavy. Okay. So now you get 25,000 joules. That is kinetic energy. So now what I am going to do is I am going to change its velocity and speed. Basically, kinetic energy will change it. How do we do it? We are going to basically accelerate it by using our rockets, okay, inside. So when you accelerate, its velocity will change. Let's see what will happen. So now it is actually currently going at 10 meters per second, and at some point in time I am going to now accelerate. So it is accelerated and gone, and the velocity it has got is basically v2. We call it as 30 meters per second. So from 10 meters to 30 meters per second, we change its velocity. Okay. Now, when we change its velocity, now the new kinetic energy is how much? Half mv square again. We substitute the values, 30 square, and we got 225,000 joules, 225,000 joules, 30 square. Okay. So now, you see, just by changing it from 10 meters to 20 meters, we changed the energy drastically, which is basically half into 500 into 900. Okay, 30 square is 900. So which will be 450 into 500, 225,000. Okay. So now you will actually look at the difference in kinetic energy. So work done is also change in kinetic energy. So how much kinetic energy changed? It went from 225,000. It went from actually 25,000 to 225,000. So final kinetic energy minus initial kinetic energy. So that would give us 200,000 joules. So work done is now actually two kinds of things we will talk about work. So what we call a work energy theorem tells us, work energy theorem tells us that work done is equal to delta P. That means work done is equal to change in the potential energy. That is in certain scenarios where an object is in the force field. And in the second scenario, work done is equal to delta Ke, where an object is in the not in the force field. Okay, we can simply calculate like that. But it is possible that both of them can be happening. It may be in the force field, and we are changing the also the kinetic energy and the potential energy. So we, in that case, basically both of them we add to get the work done. Okay. So work done and energy are related like that. And you already know that kinetic energy and potential energy are also related because total energy is always conserved. That is basically a relationship between work and energy. Now, let's look at one last thing, where let us say this person, okay, is carrying his bag and he is going to go up the stairs. So he is going to be doing some work. You know why? Because he is carrying the bag and going up. Against the gravitational pull, he is going up, and the bag has certain mass. So he will be doing some work. So let's now look at how much work he does. So we'll actually look at that he is going over the steps and goes there and stands on the top. So it actually took about 6 seconds, if I measure, for him to do that. In 6 seconds he went from there to there. Okay, now he tries it again. Okay, this time he is tired and he goes a little slowly. Okay, so he goes it now slowly goes up the stairs, and he will actually take about 12 seconds this time. Okay, now the question basically is that there is a case 1 where he took the first case, he went in 6 seconds, and in the second case where he went in 12 seconds. So did he do the same amount of work or did he do different amount of work? That is the question. The question is, in which case more work is done? Did he do more work in case 1 or in case 2? Or was it equal? That is the question. So think about it. Because in both cases, you see, he used same force and he basically used same amount of mass that he carried. Okay, so displacement is also same. That means basically force into displacement is the work done, and the work done is exactly same. So if work done, both of them are same, then what is the difference between the first case and the second case? So what we say is, in the first we introduced another parameter, okay, another variable called as power. Power in the first case is more than the second case. You know why? Because power is nothing but rate of doing work. Same amount of the work, if you do it faster, power is more. Okay, so in both cases, though work is same, okay, in the first case he did it faster, so hence the power is more. So if you look at mathematical representation of that, we will say power is simply equal to work divided by time. Let us say he did work of, let us say, about 36 joules, just for calculation purpose. So in 36 joules in 6 seconds, how much power? 36 by 6 is actually 6. So 6 watts. Watts is basically unit of power. Okay, I have not written it down here. Watts is the unit of power. And in the second case, if you see, 36 divided by 12, which is 3 watts, less power. So when you go faster, you need more power. So that is the difference. So power also is nothing but rate of consuming energy. Like at home we use this word power consumption. See, so the energy that if we actually consume energy faster, if you electrical energy, especially at home, if you switch on your air conditioner, your fans, and your TV and all the things, you will be consuming basically energy fast. So power consumption is higher, in the sense that your rate of energy consumption is higher. It is the rate of energy is power. So now we have understood work and power. We understood the relationship between work and also potential and kinetic energy. Maybe you can derive a relationship between power and potential and kinetic energy, because they are all related. You can yourself derive those relationships and see what is the relationship between power, for example, and kinetic energy. Okay. It is possible. So you know the relationship, you can try those things. So they are all the derived concepts that you can find out. Fundamental concepts are potential energy, kinetic energy, work and power. So we completed mostly everything about work, power and energy. Now what I'm going to do in the next session, okay, which is basically called energy chain, is completely different view of energy. How the energy is actually in interdisciplinary, in the sense that you use the word energy in many places, in chemistry, in physics, in biology, everywhere. Okay, so how energy goes from one place to the other place and various avatars of energy, we will try to understand in energy chain. Thank you.